So, of course, we did run a little bit tight this morning, so kind of apologize. We had to cut out the Q&A bits from several talks, and I know some of you had some. So I think maybe we'll start. Well, just kind of leave it open, but certainly now would be a good time if you want to ask questions, of particular presenters related to their talks. This would be a good time. Otherwise, we'll sort of just have it be an open discussion. I will sort of mention, if you haven't had a chance to glance at the website for the workshop and see the sort of the basic ideas that we were shooting for here. Of course, it was self-programming, and as Ben said in his talk this morning, you had a pretty wide range of things that could mean, from sort of straightforward learning on one extreme to these sort of grand vision systems that rewrite their own internal circuitry. And from the talks we had here, you had several different points along that continuum. So I think maybe we have some interesting places to start the discussion there. I think with that, I'll just open it up and let you guys start with any questions here. And the presenters, if you weren't here, there's a couple of microphones here that you can pass around if you need to. So I think I'll get everything started and sort of take a seat. So everybody want to open things up with yes, there we go.
So do you have a simulation environment for Becca? And the second part of that is, how do you program in the reward system? Could you repeat that?
Okay, so there was a question. This was specific to the Becca cognitive architectures. First question was, do I have a simulation environment? And the short answer to that is, because the interface is so simple, just passing a vector back and forth, I can interface with a number of simulation environments. Right now, I'm just doing extremely simple simulations in MATLAB. I'm looking, part of being able to interface with ROS is there are nodes for the player simulation environment, which is quite capable as well, but others could be developed. The second question was, how do I program in the reward? So in a reinforcement learning problem, an important part of it is getting a reward. And in tasks that I do, the reward is part of the task. We were talking about this over the break, a couple of us. That's something that is hard-coded and hardwired in. When you define the task, part of that definition is the reward. When you define the reward, then you define what behavior constitutes success at the task.
Tinkering with the reward function is an intelligence critical feature, and precisely that self-programming.
Okay, so the question was, is tinkering with the reward an intelligence critical feature, and if so, is that self-programming?
Well, I think, first of all, that would depend on how badly you tinkered with it, obviously. I mean, a dramatic change to your reward function could affect your intelligence a lot. Like if I change my reward function so that all I ever wanted to do was eat M&Ms, that would might make me less intelligent, depending on how easy it is to get M&Ms, right? If I change my reward function so all I wanted to do was die, then that would decrease my intelligence a lot. I'd become dead. So, but of course, a small change to the reward function wouldn't need to. I mean, I think, as I said in my talk yesterday, whether an AI system can explicitly alter its reward function or not is a design decision, and you could have a lot of self-programming certainly without doing that. I don't think that's necessary for self-programming.
Yeah, consider the effect on your intelligence of getting tenure.
May I? There are approaches that distinct between fitness and reward, and like ODR is evolving reward function, and it seems that not so much the outcome is dependent on the reward function, so it's earlier or sooner or later would come to its end, provided that fitness function is well defined. So if you make this distinction, then it's independent. If otherwise, I don't know. It's possibly dependent very much on that.
Yes. Who's that question addressed to? The question is, how would you create a new reward?
By inference in my system. By inference. Now, based on learned knowledge. Yeah, I guess I need. Well, yeah. For example, you want to reach a goal A, right? According to the system knowledge, well, B implies A. Then B become a derived goal. Okay, that thing is learned because it's not built in because this knowledge between A and B are learned by the system from its experience. Historically, yes, but in reality, yes, yes. The problem is all the knowledge which derive the new goal are the system's summary of its experience, its past experience. It's very likely to be wrong. Okay, especially when this inference chain is long enough. There is such a thing in psychology called functional autonomy. Okay, so historically, goal A is derived from B. Okay? But after that, they are handled independently in the system. So after a while, there are several things, several possibilities. One is A is still there, but B becomes stronger. Okay? B becomes the dominant goal for a certain moment, even though it's derived from A, which is happen very often in human life. Okay? For example, why these people want to do AGI? Very early, maybe it's derived goal from some other things. Okay? Some people want to save the human beings. Some people want to make more money. Some people just for fun. Okay? After a while, this goal become a goal all by itself. So in this sense, people will say, that's my goal, that's my choice. But if you check your full history, it's not, it's derived. Typically, it's derived from something else. But after that, the link is broken very often, especially if this is more than one step. Okay? And also, as an extreme situation, the derived goal may actually go back to be against the original goal. That's also very often. Okay? So as far as, go back to my basic assumption, as far as you assume your system does not have sufficient knowledge and resource to know all the consequences of your decision, to know all the future possibility, and this kind of thing become inevitable. Okay? Then at a certain moment, your goal are the one that you developed from your history, by your logic, even though it cannot be reduced to any of those things. It become your own. So briefly, usually we say, that's my goal. That's the goal I create by myself. But it's not coming from nowhere. At least that's the situation in my system.
Yeah, I think it's necessary to point out that a huge amount of human behavior is not goal-driven from the top, but is essentially an imitation of roles from role models and attachment figures. And the goals are essentially things that you found your attachment figure trying to do, and so they show up at a level below the level of high-level imitation of roles. And so to a large extent, I think that's where goals come from. And then, of course, there's sub-goals and so forth underneath that.
Yeah, I was going to say something similar and enlarge on that a bit. I think that the model of intelligent systems as reward-driven and goal-driven is a useful model, but is not a completely accurate model. I mean, human beings are not that rigorously goal-driven, whether you look at it evolutionarily or psychologically. And I think in reality, an AGI system operating with limited resources, even if it has a top-down goal hierarchy programmed into it, it's going to be a partially goal-driven system with a lot of behaviors that either due to inference errors or other spontaneous internal dynamics, the dynamics are not specifically oriented toward what the top level goals are. So given that, if you have built a system that is able to install itself with new goals, it is quite likely to, at some point, install goals that are not rigorously derived from the previous ones, either by a mistake of reasoning or by some spontaneous dynamics that aren't explicitly goal-driven. And of course, you see this in human life all the time, where people will come up with new goals that seem unrelated to the goals they start out with, and then someone at age 50 may be pursuing goals unrelated to what their 30-year-old self wanted to do or any of their friends or family wanted them to do. And I think that basic phenomenon may happen less in AI systems than in people, but logically, there's no reason it can't happen, because we're not talking about like mathematically rigorous 100% goal fulfilling systems in reality. Fulfilling goals and rewards is just a model of what these systems do.
Stephen had something.
Right. Yes, I agree. I also wanted to comment on that. I think when it comes to rewards, it's important to not mistake the map for the territory. So a simulation of a reward or a goal is not the same as having an internal reward or a goal. If we have a simulation, we want the program to operate in a certain way or towards a specific end that we imposed on it. That means that if it fails, it's basically our failure and not the failure of the program or the system. If you want a reward to be part of the program itself, that means it doesn't need any external reward function. It needs its own dynamics to be geared towards a specific end. So I think the goal, if you want an artificial system with an imminent goal, then you shouldn't expect a reward function to be sufficient. You should build the system in such a way that its dynamics are geared toward that goal.
May I comment on it? The same?
Sorry, go ahead, yeah.
Yeah. I believe we use a little bit different approach, and we try to design a universal reward function, which is intrinsic reward, and all goals would be just dependent on that reward, which is purely information theoretic approach, and we want just to say that what is rewarding is the same as what is where you gain information. When you gain information, you get a reward, and it's not the only approach. It's like Schmidt-Huber is doing compression progress approach for intrinsic rewards. So there are these approaches where there's a attempt to make an intrinsic reward a universal one that is built in, and all the goals that you can imagine are just only cases of this information hungry proceeding. So that's our approach.
So in this conversation, it's useful to make a distinction that I think often goes unmentioned in this community, which is there's two goals that can be orthogonal. One is creating artifacts that do something really cool, and one is creating artifacts that behave in the same way, using the same mechanisms as the human brain. So modeling the brain or performing on tasks. And I think most of us hope to be able to do both, but there are many instances where you can do one without doing the other. And so in the instance of rewards, there's two questions. There's one is, how does the human brain do it? And how do animal brains do it? And the other is, using rewards, can I get artifacts to do what I want them to do one way or another? And I think that's what I'm hearing is two sides of that in these comments.
That's right.
This question is directed at both Becca and Adriana. And the question is, well, from my perspective, I saw some similarity in those two architectures, and I was wondering if you see that similarity as well, if those two systems could possibly be compatible theories, or whether you think there are important differences in your two approaches.
I didn't know the other approach before this conference, so of all the speeches, this was closest to what we are doing, but to compare, I think we should make more more comparisons. I'm not sure if you are now doing it in real environment, in real time, so that may be a difference. But in general, reinforcement learning is one of the approaches that is quite common. But how is self-programming? It's quite different in all these approaches. So
Yeah, this is also my first exposure to AGI now, so it would probably require some more talking to answer that question in detail. I mean, in general, they're both cognitive architectures, and there's a number of approaches that fit within this same broad category. Yesterday, we heard a great description of the LIDA architecture, which also, has a number of similarities. And in general, anytime you have an agent interacting with the world, a lot of things are likely to look the same. So there probably are some similarities. I think the small differences in the details, all of us who are working in this area and developing in this area, we don't know yet what's going to work the best. So we're all kind of pursuing different answers and cherry picking from each other, trying to pick what works best and come out with something really neat.
Okay, we had a question here and then one in the back.
Yeah, I have one more comment on that. I think one possible way to parse the different kinds of approaches to AGI is to say that at the very, very highest level, everybody is trying to imitate a human intelligence in a very abstract sense. And what you want to look at is how far down they go before they cut over to an engineering approach. And I think you can actually get a spectrum, simply saying, okay, we want to get just the notion of intelligence, or the notion of intelligence with certain human-like characteristics, or we're going to try and re-engineer the functions of V1, V2, the particular parts of the brain architectures, if we know them, all the way down to we're going to simulate individual neurons. And there's just a whole host of different cutoffs in between. But I think that a lot of the different approaches you can look at in terms of just saying, okay, how far down do we go before we cut over to engineering?
Yeah, I don't necessarily agree, because I think that captures one aspect of what happens in AGI, but there are also respects in which many of us are explicitly not trying to do what the human brain does or what the human mind does. I mean, I think there's also a strain of trying to go beyond what the human brain is capable of, even in the architecture. And this business of goals and rewards ties into that, because I think a system like OpenCog tries to be more rigorously goal-directed than I think the human brain is. And I see that as a feature rather than a bug, because I would like powerful AGI systems to have more of a tendency to direct their actions toward their initial goals than people have. So it's not all about trying to emulate the human mind brain, unless you construe that very, very, very broadly. Right?
Well, I think actually what you've done is to find an abstraction above the actual human brain, sort of like an angelic or something. That is
hopefully angelic rather than
yeah,
demonic.
exactly. But it's sort of an ideal human, which none of us actually is, and that's what you're. And so
I don't think of it.
Yeah.
I don't think of it as trying to make an ideal human. I just think of it as trying to engineer a different sort of mind.
Well, an ideal intelligence.
That's AIXI, but you need an infinite computer for it, right?
What can you say?
All right, let me add a few words. Actually, on this topic, I agree with Josh. I think it's also, no matter what you do, we have a lot of difference, right? But still, we think, even Ben think in some sense it's a mind. Also, that in that sense is similar to the human mind. It just say that below that level, I don't care. It just, like Josh said, where you cut. Actually, I want to mention that in AGI 08, okay, I have a paper just on this topic. It's called "What do you mean by AI?" In that paper, I define 5 different levels, okay, to try to capture a different perspective about at which level AI should be similar to the human mind. And below that, everyone say that below that, I don't care. Okay, our difference is kind of like that. Maybe not necessarily 5 level, but something like that.
All right, so I had a question.
Something I saw in common with a number of your presentations, that getting the self-programming by getting the higher levels of abstraction, either by refactoring or reasoning or seeing patterns within patterns within patterns. Does that of these things common to some of your approaches?
If I would take creativity as my approach, at least in this presentation, the general idea of creativity is that you ignore certain differences on a higher level so that things become alike and you're able to transfer from one system to another system. So to transfer the knowledge of one system to another system. So that's a technique that's common in recognition, for instance, where we ignore certain differences between objects in order to say that they're alike or say that they're of the same class. And in terms of creativity, you're doing that on a higher order. So Einstein was able to ignore certain differences, making that his theories. He was able to ignore some certain differences so that his theories of physics could become geometrical, for instance. Or if you think about art, and I'm talking about the eminent sciences right now because those are the best examples that we have. Ignoring certain physical differences would allow you to go beyond just picturing them realistically, and then picture so that you can picture them imaginatively. So I think in that approach, there's definitely an element of going to a higher order level, and then seeing differences and similarities right there.
Sure.
This one's for Dr. Hall. You had a system where you take a look at what people are doing and reason from the remembered situation or the present situation into something that you should be doing when the people are successful. If you have somebody who is performing a non-deterministic action and they fail, maybe like shooting a basket into a basketball hoop, can you reason from failures of actions as well as successful actions? And if so, how do you know which people to copy off of and which people not to copy off of?
Well, the short answer is you copy off of the ones who get rich, powerful, and lots of women, and you don't copy off of the ones who get laughed at. At least that seems to be the human heuristic.
Rich, powerful stand-up comedian.
Yeah. But yeah, we have a bunch of built-in heuristics that form some of our basic motivations that stand for that in the human mind. And there's clearly a version of that hierarchy and imitation thing that is the aversive side of this. You match for bad outcomes and avoid doing whatever it is that your theory of causality tells you led to it. And sometimes that works and sometimes not. But yeah, I mean, I didn't have time enough to give the whole the whole spiel there, but that's clearly something that the system has to take account of.
Yeah, Ryan.
Ben introduced a measure of self-programming, and I think the first component was the amount of change in the element, and the second component was the importance of...
Well, it was an attempt to define the extent to which a given act of learning is an act of self-programming. So there were two components. One, how much is learned about X. The other is how intelligence critical is that thing X that was learned about. Right.
So the first one seems easy to compute, but the second one seems a lot harder. So I just thought, does the panel have any opinion on that? Because for me, I would think, well, if you make a change to an AGI, one way to test how valuable it is to make a copy, run that AGI in maybe a battery of tests and say, oh, was that a good thing? But of course, you can't do that for all possible cases. You know if that was really a good decision.
Yeah, so to tell how intelligence critical a given act of learning is, first of all, you need a measure of the intelligence of the system. And then you need to somehow estimate like what was the causal impact of that given act of learning on the intelligence of the system. And in the case where you could create an ensemble of systems, so you have an AI system at your computer and it learns something at midnight, you could kind of freeze it at 11:59 and look at a bunch of systems that didn't learn that thing and a bunch that did learn that thing. You could calculate the intelligence of each system in the ensemble, and then you can get some quantitative sense of how critical that particular act of learning was for the intelligence of the system. But if you're dealing with a singular system, like a person or something where you can't make an ensemble and do that experiment, then you have to use reasoning of some kind to indirectly infer the intelligence criticality, which is a hard problem, right? I mean, qualitatively, we seem to be able to do it in everyday examples, though, right? So I mean, like if you learn the meaning of some new words in the Serbo-Croatian language versus you learn some new strategies for doing scientific experiments that you then kind of can generalize to other things. It may be, we have a sense that the latter is probably more intelligence critical than the former, which is based on kind of intuitive reasoning rather than rigorous reasoning. And to do that kind of reasoning rigorously, of course, is hard. But I guess in educational theory, they try to do that, right? Because one of the goals there would be to improve the performance on standardized tests of students. And they try to teach various things, and they do have some idea of which things you can teach kids to improve their problem-solving ability and intelligence. And there's been some idea that progressive education, teaching children to problem solve, works better than just rote memory, for example. They decide that problem-solving skills are more intelligence critical than memorizing lists of facts. So there seems to be some tradition of making this kind of judgment qualitatively, but it's not very rigorous.
On the same topic, because I would like to return to the question of what we call self-programming, because for me, programming is like that there must be something like Turing complete or not necessarily Turing complete machine and the code that is executed, because otherwise that's learning, some type of learning or fitting. And so when we use this term self-programming, do we mean execution of some programs or program-like structures, or do we mean something more like I think Ben wants to introduce here? It's this question on naming convention just.
Well, according to the definition I suggested, pretty much any act of learning would be self-programming to some minuscule degree, and it then becomes fuzzy. So a really strong example of self-programming, of course, would be some system that actually revised the source code underlying its core algorithms, and that would have a very high fuzzy degree of self-programming by the definition of I proposed. Whereas learning some random fact about the world, since that fact has very low intelligence criticality, would have a very low degree of self-programming. And whether something involves learning a program or not, also that seems a difficult thing to define, because if you have a system like a brain, I mean, we can model it as a program or as learning programs in various ways. But then whether something is a program or is program learning a lot, it's largely a matter of how you choose to model that system rather than the system itself.
I would say that one way of thinking about what it means to program is simply what it takes to go from saying what to do to saying how to do it.
Yeah, I kind of have the same reaction as him about Ben's suggestion. I think Ben's idea is interesting, but I will say it's more proper to be called something as the significance of learning. For a certain learning result, it can be important, it can be trivial. You want to measure how important it is. It's not really limited to self-programming, and it can be fully applied to declarative knowledge learning. But usually we say declarative knowledge learning is, well, of course, it's also related to self-programming, but it's kind of like more remotely or indirectly.
Okay, so I have a question for everyone on the panel then. What do each of you mean by self-programming?
I already mentioned that in my talk.
Well, can you summarize in like one sentence?
Put actions together into bigger chunk.
Put
Into
action,
scales.
so just chunking is self-programming. Then why call it
Some-
self-programming instead of chunking?
Well, that's what we mean by programming, at least to me. Okay, what programming means? Every day we do programming. That's what we do. To me, well, every concept is fuzzy. Okay, but if
Sure.
you make it too fuzzy, it become, if we cover everything, it covers nothing.
But every example of chunking, every example of chunking
I'm
is
not going to call it
self-programming?
chunking. I will just
Okay.
say programming. Well, in the intuitive sense.
But then all programming is self-programming.
No.
But if any.
Well, this computer, I can program it. It doesn't program itself.
Okay.
In that common everyday
Okay.
sense of programming.
Okay, but is there learning which is not self-programming then?
Yeah. Learning declarative knowledge is not directly related to self-programming, but it is indirectly.
So you assume
related.
a rigorous distinction between declarative and procedural knowledge.
Yes.
So what
Yes.
if you had an AI system that doesn't have that kind of distinction built into it?
At a certain level of description, it will. As far as you stay with a certain level of virtual machine, that's what I mentioned. Your example is when you move from one virtual machine to another, program at one level become data at another level.
So
Of
if you,
course,
if you have a system which is, say, some kind of big self-organizing neural net, which seems to have no distinction between declarative and procedural knowledge, what you would say is you want to model it at a level that distinguishes declarative and procedural knowledge.
Yes.
And then only the learning of procedural knowledge is self-programming.
Yes.
But
yes, I want it to be narrow enough so that we can talk about it concretely.
don't you think sometimes it could be very hard to model the system in that
it's true.
in that
it's just
way?
like you can say every concept is fuzzy. If you want to push that far, then every concept can be exchanged with each other. It become.
Then
I
we're
don't,
all
I don't see
enlightened.
that as very interesting. But it's a matter of how to use the word.
Does anyone have a different concept of self-programming that hasn't already said it?
I believe I said already. Yeah.
Yeah, we're building up quite the queue of questions here. So
How about jargon?
I promise him one. Well, Jack, go ahead.
I can pick up that
Maybe-
question, I think.
Maybe we'll put that on hold for 1 second because he's dying to say something that they were just talking about. So then we'll come. Yeah.
Just a short hint. That is a scholar-heavier article about meta-learning, and it's not calling that programming and self-programming, but making the distinction between meta-learning and learning and adaptation. So there's a source of material that one should probably use. The first author is Tom Charles, who is sitting over there. It's exactly about the questions that are being addressed here.
I think that emotion in AI systems is a pretty big topic, which is kind of a digression from self-programming. So,
I think I can say something short about it that relates to my talk. So, I think emotion has a lot to do with the energetic constraints that I mentioned in my talk. So, emotion is one way of diverting from a path that has been defined by a program. And it's not a programmatic way of diverting from a path because it has to do with the energy that's available in the system and the tension that arises from the required energy and the energy that is available. So I'll stick with that.
All right,
So I'd kind of like to go back to the sort of fuzziness of the metric that Ben was coming up with. I'm wondering if there isn't some sort of uncertainty principle here, because it seems like the higher the degree of intelligence criticality, the higher the degree of uncertainty.
you mean the unpredictability of the result of that self-modification? Like if I change my reasoning algorithm, it's harder for me to predict what's going to become of it than if I change my understanding of how to parse Serbo-Croatian verbs or something, right?
The more potential usefulness of the particular thing that you're calculating, the more useless it becomes.
Why do you say the more useless? I mean, it seems like the more volatile the outcome, but that doesn't necessarily mean more useless, right?
Well, if the outcome is so volatile that you're not getting any information content out of it.
Well, but just empirically, in terms of human common sense, it seems not true, right? Like learning how to solve problems or learning how to reason using Bayesian inference better, it may be unpredictable what the outcome is because it could lead you in a lot of directions you didn't expect before, but it doesn't seem to be so unpredictable that it makes you go jump off a building or run off into the woods and become a primitive or do completely crazy things, right? So it seems like in human life, it's not true. We can learn intelligence critical things and it's not that volatile, as you say, though it is more unpredictable than learning new words or something. So, but I think you're probably right that there is some result there, that the more intelligence critical and active learning is, the harder it is for the system to predict exactly what will come of it. But maybe not as extreme as what you're implying.
A question for Josh. You write about the importance of plastic representations. I'm curious if you have any ideas about how we're going to go with that to relate to your generalization of analogical questions.
Well, I'm not sure I understand what the question is here. I think I mean, the point was that a plastic representation, one where you can force a match in a way that causes you to see what it was you thought you were looking at in a different light, and that you can translate that different light onto the action in such a way that you get a different action, is key. Is just you can't do the operation without it, or else your ability to imitate would only be purely and exactly literal imitation of what you had seen. Okay. Yeah. Well, the examples I talked about in the paper are essentially being able to knock out unsalient attributes of things that you're operating with in favor of salient ones. For example, if you're trying to put if you see someone putting a small red block on a big green block and you're supposed to imitate that, but all you have is a small red block and a big green block, then you have to ignore the color and use the size. Yeah, at the level where you're parsing things into objects with features like that, that's exactly what it means. At another level, for example, if you're imitating somebody and you have a different kind of arm than they have, okay, you have to be able to ignore the fact that they're using a human hand and use your two-finger gripper instead, and have to be able to map what causes the desired effect, namely grasping and lifting a block, in terms of your own equipment. And so there's lots of different kinds of mappings that are necessary. And the stuff I'm doing, which is really very difficult and hard to describe, is trying to force things like numeric vector representations to capture salient features so that you can do quadrature with vectors. And I'm not even sure that that's possible, but that's what I'm shooting at.
This question is for the whole panel, and it has to do with exploration. In most reinforcement learning frameworks, there's a clear distinction between choosing actions that are exploratory versus choosing actions based on the current knowledge of the system. And often this is done in a way where exploratory actions do not disturb the knowledge of the system. It seems if you have another sort of framework that involves self-programming, that you run the risk of changing the program in an exploratory way that then is not easily reverted. So I'm curious across these different frameworks whether there's any support or reversion or undo of exploratory changes?
With mine, it's pretty easy. You just erase the most recent memories.
Well, I think on a mechanical level, that's easy because the system saves its state periodically to disk. So the question is more in an autonomous, self-motivated system. After it changes its motivational system, maybe it doesn't want to undo and go back to what it was before, which is the really subtle question. I don't think there's really a workaround for that. I think that's a feature rather than a bug.
There's no mechanism for that in my work either. There's I mean, you and I, there are lots of exploratory things that we can do that can never be undone as well. So one might just argue that's part of interacting with the world.
Yeah, in my system, you can partially undo something. Say at the beginning you think A is better than B, and you try it, it turns out to be the otherwise. Then you prefer B, and after a while you change your mind back. Say you think B is better than A, and then the other way around. But you never exactly go back to a previous state. You always have accumulated evidence. But partially you can switch your preference.
I wonder if I understand your question, because it's everything is flexible, and once if there's exploratory action and it is not rewarding after shorter or longer time, then it's discarded, or at least this route of state action is discarded. So there's no. It may be only. Just for some time may lose some resources. The system may lose some resources of doing some action that is non-optimal, but this is the question of exploration, to do something that is non-optimal to possibly maybe find not local maxima but global maxima, and so there's no problem with discarding these exploratory actions. So.
Right. Well, in relation to my talk, I think it was mostly about that problem. So what do you do when exploration has sort of fails, and whether you're able to transform a search space, and if, you know, when you should start doing that, and how do you do that? What I could add to that is that exploration is always changing the system in some ways, in that it takes time and energy to explore. So the system is never in exactly the same state. So just by doing explorations, you change the system in some way, although it might be minuscule. If you transform the system itself, it's a large change. If it's just small exploratory steps, it's a minor change.
Well, it's the first time I have a chance to speak in this panel, but on these specific questions, my system is a little different. Is this working? Yeah. There is a direct relationship between knowledge and results. So reward, the concept, okay, first I should say some of the concepts that have been developed during the engineering of intelligent systems do not map quite directly. So I'm doing a little bit of guessing. But I believe that the notion of reward belongs in the input to the system, that is the knowledge. So it would be an act of learning. And when this act of learning occurs, then there would be an automatic response, autonomous response from the system by creating those structures I have been speaking about. And those structures are the ones that have an intelligent critical value useful for intelligence, that would be it basically. The other comment that is also somewhat related is that I would like to see some more emphasis on the self of self-programming. I am plenty satisfied with the programming part. We've been talking about programming a lot. But somehow I see that there is some underlying feeling that we are the ones who are going to do it, not the autonomous system. So if we talk about the autonomous system, we should emphasize the self part a lot more. It's not us doing it, it's the system doing it. So how does the system do it? Well, that's the talk I presented.
So I'm going to abuse my moderator privileges and follow up there. um, sort of a follow up. So obviously there's a pretty big discrepancy on what we classify as self-programming versus learning. But if we pick something that is sort of far enough along the scale that everyone would agree to call it self-programming, then we seem to naturally think of that as being sort of at the top of your pyramid, right? You get that after your system has been essentially reached a level in which it's capable of introspection, and it's not just making arbitrary changes. It has some theory. I'm going to change this about myself because of something that it knows. Do we think that there's any value or any help in sort of decoupling those and having the ability to modify the system? Obviously, you need in the absence of a theory of learning.
Decoupling which two things?
This sort of underlying theory of why I'm making this change versus making the change itself. So in other words, if I took something like genetic programming, it's rewriting source code for some. It's not self-programming because it's generating something, but it's making these changes with no underlying idea of why it's doing it. Is there some value in sort of building up to a self with a system that includes the ability to modify its own architecture, even if it's doing so essentially at random and then getting feedback as to what worked? In other words, rather than putting it at the top of the framework, can we put it somewhere near the bottom? Can you build a toddler with a system that has self-programming, even though it doesn't have enough knowledge about itself to know beforehand why that change would be good?
So you're asking the extent to which fairly strong, like reflection-oriented self-programming could be useful even in the early stages of the Piagetian hierarchy?
Yeah, in a manner of speaking.
I mean,
without the sort of the introspection part. In other words, it's making these changes that are extremely significant, but it doesn't necessarily know beforehand that it needs to do it for some reason.
It seems that in human development, many profound changes occur during the first few years, but a lot of these seem to be like genetically triggered rather than through the system's own thinking. I guess I kind of think that a baby or a young human child or an early stage AGI system lacks the intelligence and the breadth of knowledge to think about its own thinking very significantly and figure out how to modify itself. So I guess my gut feeling is that kind of deep, profound self-modification and self-programming, to my mind, is something that probably can only be profitably undertaken by a fairly mature system. Like thinking about my kids when they were little, when they were like 3 years old, they were learning a lot about the world, but they weren't doing a lot of reflecting on their own cognitive processes and how to improve their own cognitive processes in some kind of deliberative way. They were learning and adapting, right? And then once you get older, like you get into high school or college, maybe you start to think like, well, I'm better at proving this kind of theorem than that one. How can I adapt my theorem proving process and my learning process better? But to me, I feel like that comes fairly long in the hierarchy, but maybe that's overfitting to human development.
I was about to say, I think clearly humans do that.
Yeah, maybe there's a whole different way of doing cognitive development in AI systems, much less similar to how humans do it, that would kind of use self-programming at the beginning to bootstrap itself. I think Steve Omohundro was working on that some years ago. Actually, I don't know. Do you have any comments on that?
It was a whole big long story.
Yeah.
An agent which is behaving in a rational way is not going to want to change itself willy-nilly. It's not going to want to make a change that's going to dramatically affect its future. That's going to be probably the most important decision in its entire existence. And so if it's behaving rationally, it's going to do that very, very carefully. And it will develop the reasoning ability to be sure that what it does actually aligns with its goals.
So you were thinking about or working on a system that would kind of bootstrap by self-learning and self-modifying. Is that right?
Any sufficiently intelligent system is going to realize that it can improve itself by changing its own code. It's just going to want to do that. And so pretty much any AGI that's sufficiently powerful is going to want to be a self-modifying system. And it's going to want to be careful with it.
Yeah, it's a matter of what sufficiently powerful is. Because I would say a 2-year-old kid doesn't want to be a self-modifying system explicitly because they don't know what the hell that means.
But nor
right?
would a 2-year-old kid be that careful about it.
I have a major objection to this whole. I have a major objection to this whole line of talk. I don't think there's a qualitative difference between learning about self-awareness and meta learning and so forth than just plain learning. I think essentially what happens is that as you learn, you fill in levels of your ontology hierarchy. And you can't fill in the higher ones until you fill in the lower ones for them to have concepts to latch to and refer to. So that as you grow mentally, you're always learning new things and you're always programming yourself by adding new rules to your code base, essentially. And once you get to the point where you're explicitly reasoning about yourself, you're just doing the same kind of thing you've done a lot of before at a higher level. And what's happened is that these rules allow you to operate what's essentially a world model. And at some point in the Piagetian hierarchy, you start including a model of yourself in the world model. But I don't think it's a qualitatively different thing than what goes on in the whole rest of the process.
Yeah, that's
I may comment on that, please.
Let's hear what Jürgen has to say. The Gödel machine solves everything.
I just would say that thinking of your kids with whom you mentioned, that they very early in their life start programming themselves. Why? Well, they have some internal head rule or whatever it is going on, which makes them associate the things they see. But they selectively choose the data they see. They look here and not there. They do all these things that lead to certain types of internal wirings, which are different from those that they would get if they looked in other places. And so you have, even if you don't know exactly how the head rule that you're using in your neurons is working, or whatever learning rule it is, you nevertheless can use it all the time for self-programming. And that's what everybody is doing all the time from very, very early stage in his life. So I would say there is a huge amount of self-programming going on since, probably even before your birth.
Here.
There's a whole sequence of
of
systems that since 20 years have tried to imitate.
Well, in that broad sense, you're definitely right. But then the line between self-programming and learning gets blurry. And I thought he was specifically asking about a more kind of
so this phenomenon has
deliberative, rationally guided kind of self-programming.
This phenomenon has actually been observed in some of the simulations that I run. As it goes to achieve its goal, it spends a lot of time around the goal, and as a result, the features associated with that goal get populated much more richly.
Yeah, and I mean, for 20 years, there have been lots of observations like that, yes.
Well, you know that there is a very strong movement now in the field of neuroscience that refers to the unconscious. They called it the other one in me. And what they basically are saying is that there is most of what we do, most of our actions and decisions are entirely unknown to us. So we don't know who is making our decisions or how they are made. There is a big part, a substantially important part of our brain that is working automatically and in complete disconnection from our cognition. That part is what I claim is exactly, precisely, the emergent inference. That part is the one that does the learning, that does the processing, and then creates and generates the intelligent structures that then it delivers to cognition for use in probably a reward system. People can control that. You can program your subconscious, ask questions from it, give information to it, and it will tell you, for example, in the Piagetian hierarchy, as the learning process proceeds, it will tell you the different stages that happen in the hierarchy.
We had a question, Javier, and then next is...
Yes. Mine
My view of this problem of self-programming, of learning, is that every system has a kind of limit where you can not go further and modify. So there is a lower limit of your architecture where you cannot modify down than that. And it's depend on where is this line, if it is learning of self-programming. For example, if the algorithms for learning or actions are fixed and you only have parameters for those, or you can learn the parameters of those, well, you can view this as learning of self-programming. If you can change or change the preference for these actions, so maybe it looks more like self-programming. But in one sense, there are one level in any system that you cannot modify down than that. And when Dion asked if this limit could be the evaluation of the action of the self-programming in, in itself. Well, this is my point of view, and I want to see what is the opinion.
This is Hofstadter's argument too, that he says that there is some level you can go below, but the same is in nature, physics. You can't even change the speed of light by a tiny portion because you lose everything. And what we are trying to do is to build on top of this, but we cannot change, a system that is close to Turing complete machine. And if you have a Turing complete machine that is fully flexible, then you can virtually do everything. And that's an approach, that's a solution. So there's no this limit of what happens below.
Let's try and get as many more questions here as we can. So a couple here, and then I know we've got one here. So yeah.
So my question was basically prompted by this discussion that we did in Europe, which is this idea that part of self-programming, or say a reinforcement learning system, might be having it act in a way which tends to change the environment in a way which alters the set of rewards. So for a classification system, it tends to change its attention in a way that the input patterns of its learning alter. So given that, would you view any system which is doing active learning as actually actively selecting its inputs for whatever low-level learning it's doing as a self-programming system, or is that still below the threshold?
Well, in my own perspective, as I presented my talk, there wasn't a threshold, and I was just looking at self-programming as learning of intelligence critical system features. So in that approach, you don't need to make a choice of what's cognitive content and what's infrastructure or what's declarative or what's procedural. So in that sense, yeah, an active learning system could conduct intelligence critical learning just by putting itself in a different environment. Yeah. Well, no, because depending on your AGI system, a system could use different sorts of processes for more intelligence critical learning than for other kinds of learning, which might be rational if what he says is correct. If learning intelligence critical features has more volatile results and is more likely to screw you up, you might want to be more careful about it, so that you could have different processes for that. And I don't actually think that's necessary based on what I understand so far, but it might be. We're not nearly there yet in terms of playing with it with our systems. Getting back to little children, I mean, you could see that there's a lot of reasons why little children are small and weak and can't cause a lot of damage, right? Because they're, in a way, that their intelligence critical functions are changing all the time and in quite volatile ways. And because they're small and protected by others, they can get away with a lot of volatility. And we're supposed to be more stable. Our intelligence critical features are not supposed to be changing so much, so we're expected to behave in a more reliable way, right? So.
All right. So we had one there, and then here. So, yeah.
I'm wondering if, I think this is for the whole panel. There's not too much more logic going on. There's reference again and again to child development. Are we sure that cognitive architecture is all going to develop the way that a genetically programmed brain, fast brain growing child is going to develop? I think that's a big mistake. A and B, then you start bring an emotion, then you basically, left the whole realm to me of artificial intelligence. Now we're talking about, we're really just always talking about human intelligence. That's my first comment. My question is, as in any architecture, as a system becomes more self-programming and self-improving, especially the intelligence critical parts, as Steve Omohundro has written, does it migrate towards rationality? Because in order to make decisions that are good, in order to improve, it's got to have a model of itself. It's got to have some self-awareness, and it's got to become increasingly rational. And as it improves, it becomes increasingly rational again. So those are kind of two comments and questions.
Well, ontogeny recapitulates phylogeny, and so if you have a theory of the brain that's based on an evolutionary story, you're almost willy-nilly going to talk about the development of the individual intelligence along a similar pathway, and that's the way mine works out. Now, of course, that's not the only way it can be done, and I'll let anybody else that is doing it differently.
I think you make a really good point that for most of us, either explicitly or implicitly, we rely heavily on introspection, our ideas about how we think and our ideas about how we acquire that intelligence. If you take that away, a lot of us are left without a basis for what we do. And it's something that bears careful inspection for anyone working in a cognitive architecture.
All right, so over here, sorry.
My question is going back to that topic of invariance. The idea of saying there's something that doesn't get changed. And so if I go further than that, I can imagine very simple algorithms that generate random programming, simpler than generic programming. They can obviously produce any possible solution to a problem. The function, say, keeping simplification of machine learning, we want to create a function from input to output. Be a situated agent, mapping states to actions, learning a policy. So we can obviously make systems that can learn anything. And so creating arbitrary programs. Now, obviously, that could be very stupid algorithms that might need to be changed. And to me, it seems like there's a relationship between the subject of constraints brought up by the name out of the box. There's related issue of constraints about if I make this algorithm be faster, more efficient, it might be unable to do certain things, whereas if I make something slower, maybe it could solve any puzzle problem. Would that be a sort of a goal in why you'd want to have self-modification past the ability to learn any arbitrary function? I mean, what would be the goal of further levels of self-programming?
So I'm going to go back to his question briefly. I think that human cognitive development is certainly not the only path to AGI. It's just the only path that I understand well, which is why I'm using it as a guide. And in terms of smarter and smarter systems as they self-program, necessarily becoming more and more rational, I think that's highly uncertain, because the theory of rationality under limited computing resources is just not that clear. So that's one thing that could happen, but the circumstances under which it would happen are not that clear to me, and have a lot to do with the situations the AGI is in too. I'll leave it to someone else to answer his question.
Right, so the question there was basically why self-programming, right?
Yeah, why self-programming? Is it efficiency? Is it
it's fun.
Well, for me, I can try to answer that question. So the question has been raised a couple of times before, whether there's a difference between learning and self-programming in general. I think self-programming is a special kind of learning, and that's interesting because it requires two things. It requires a self and it requires a program. And I think, as you already mentioned, rightfully, the focus has been a lot on the program and not so much on the self. What I personally find interesting in the concept of self-programming is that it forces you to think outside of programs. So as I tried to demonstrate in my talk, you can't have a program programming a program because that's just a program. So you need something else that makes programs. What could that thing be? Well, it has to be itself. Then what defines a self? I think the best definition of a self is something that has a goal of its own. So not something that has been given a goal by means of a reward function or something, but something that's then dynamically structured so that it tries to achieve a certain goal. Those are the questions that I see coming out of self-programming, and those are the questions that interest me personally. So.
As Ralph Waldo Emerson would have put it, code thyself.
All right, so I think we're nudging up against lunch here. So that was an excellent way to end, I think. So thank the panel, everyone.